Hello friends, we have already seen how to propagate the errors in case of addition, subtraction, multiplication, division and power functions. Here we will try to understand how we propagate the errors when our functions they become slightly more complex. So for example, if I have the value of theta, which it's an angle which I have measured to an accuracy of 5 degrees, and I want to compute sine theta from it. So obviously sine theta computing is not very difficult. We can compute sine of 30 degrees. That's not the issue here. But the real problem is, how does the error of 5 degrees in theta translate to the error in sine theta? So we really don't have a mechanism of computing that yet. So in this class, we will understand how to do that. So here we have an arbitrary function of x called qx, and this function of qx we have plotted against x. So this is x right here and this is q right here, and so here we have plotted the qx. We'll try to understand for this x best here in our example is 30 degrees, and this delta x is our error on either side, which in our case is 5 degrees. This qx, in our case, we have taken it to be the sine theta or sine x, whatever you want to call it. And we want to know, what does this 5 degrees, this delta x, translate to in terms of sine theta? That's our objective. What does it translate to in terms of sine theta, or what is this delta q right here? So to compute it, first thing, understand that at this point, the slope of the curve, which is the rate of change of q with respect to x, which tells me how much does q change when I change x, is for a unit change in x, is given by dq by dx. So it's just the differentiation of q with respect to x. So that is the slope at this point. Now, since this delta x is very small, this error hopefully is very small when compared to my value of x, when compared to x, it means that I can assume that the slope would remain constant all throughout. Therefore, I can compute this delta q to be just this slope dq by dx, which tells me the rate of change of q with respect to x. So for a unit change in x, this is the change in q. So for a delta x change in x, this will be my change in q. Okay, so we are just using this formula, the derivative formula dq by dx, to translate the error in x into the error in q. Okay, so that is a very simple idea behind this entire video. So let's take an example so that we can firmly ground this idea. So here we have the value of theta computed as 20 plus minus 3 degrees. Okay, so everything here is computed in terms of degrees, and we want to find out the error in cos theta, or in other words, we want to write down cos theta in terms of the value which is q plus minus delta q. Okay, that is what we want to write down cos theta as. So here we know that our q is cos theta. This is very simple, nothing complicated. We have just given it a name, the function a name, and we know that delta q is nothing but dq by d theta, multiply it with delta theta. Okay, so the small change in theta, the error in theta, if you multiply with rate of change of q with respect to theta, we will get the error in q. Okay, so the first order of business is to really compute dq by d theta. Now see, the thing here is, the one thing that we have to remember always, as soon as we are going into the differentiation of angles, differentiation of trigonometric functions, as soon as we do that, we have to make a habit of converting our degrees to radians. Okay, because if we don't convert our degrees to radians when differentiating or integrating the trigonometric functions, we will end up into trouble. So first thing we do is that we convert this into radians, which is of course very simple. It is not very difficult. So we write it as 20 plus minus pi by 180 into 3, and this now is of course in radians. Okay, Nothing difficult, that's what we have done. So now we can go on to differentiate, and differentiation is of course not very difficult. It is just the cos theta's differentiation is sine theta, and here we are only interested in the absolute value. Okay, so we have just ignored the sign here there completely, the result of the differentiation. We are only interested in magnitude. So think about this. When we are dealing with errors, we are only interested in the magnitude of this quantity. We will be using the error on either side. So we are not really a plus minus we will be doing. Okay, so we don't really need the sign of this delta q. We're not really interested in that. We only want the magnitude. So here we can completely ignore the sign of this differentiation, whatever it be. So here we only are interested in the sine theta, the value of the magnitude. So that comes out to be very, very simple. And now if we plug this in, what do we get? Sine of pi by 180 into 20. Okay, so that is my theta. Okay, so not very difficult, but of course we are not interested in this. We are interested in delta q. Okay, so we will write that complete thing right here. So delta q is actually equal to this thing, dq by d theta multiplied by delta theta, and this of course is, we will be multiplying it with this number, which is pi by 180 into 3. Okay, so that is what, this is our error. Okay, so this is the error term. So we have shown it in green right there. So that delta theta is what comes here. So this is delta theta comes here, and we multiply it with the differentiation of dq by d theta. So that's what we have done. And if you compute this, this comes out to be plus minus. We will not write plus minus right now, but we'll simply write the value 0.02. So that is our error in computation of cos theta. That is the delta q. This is the error. And of course we know the value of cos theta, which is cos 20. That comes out to be 0.94. Okay, so cos theta is 0.94. So our final answer would thus become, so if you are interested in the final answer, that would become 0.94 plus minus 0.02. So that is the final answer, that is the of cos theta. So error computed separately always. Okay, so error we have computed separately here, right here. This entire thing is the computation of the error delta q, and the function, the value of the function itself calculated separately, which is typically very, very simple. So calculation of the function itself, cos theta is just cos 20 degrees, which is very, very simple, 0.94. That is not difficult. Compute the error separately. For that you will have to do some work, but again, if you approach it systematically, it's not very difficult, and this is our final answer, like we said. Now, so far so good. We have looked at the function of a single variable. So single variable, we know how to deal with that. Now here what we have is, we have a function of multiple variables. We have two variables right here, which is x and y. So q is a function of two variables. So how do we deal with this? See, for that what we need to do is that, if you have not seen the video on partial differentiation, you should definitely watch that. But the idea is, the error in q has two components, if you think about it. Okay, there will be, the error in q will be because of the error in x and because of the error in y, because q is a function of both x and y, and both x and y have been measured. They are both measured quantities. None of them is really constant. Both of them have errors. So this error in q, this delta q, will really have two components. One is the error because of x plus the error because of y. Very, very simple. Now, what about the error in x? The error in x, delta qx, we already know that it is nothing but the partial differentiation of q, del q by del x, which tells me the rate of change of q when with respect to x, when y is kept constant. So this is what it is telling me, the rate of change of q only with respect to x multiplied with delta x. Okay, so this is the sign of partial differentiation, and similarly delta q y is nothing but del q by del y multiplied with delta y. Okay, so it is the error only due to y. Now if I sum those two, then I get my total error. So my total error is just the sum of these two. So that is the concept that we will be using. Very, very simple. Okay, nothing complicated. Very, very simple. Okay. But the idea is that both of these, we have to only focus on the absolute values. That's something that we really have to understand. So we will put the absolute value sign here so that things remain very, very clear. Our rate of change, we are only interested in the rate of change in positive direction. We will only take the absolute value, because both of these, we only need to be concerned about the magnitude. We are not really concerned about the sign of the differentiation. Now to compute this, first we differentiate this with respect to x. So holding the y constant. So y we are assuming it is constant. So now we can write our delta q is actually equal to del q partial differentiation of q with respect to x. So that is 2xy. Y is just a constant. We are just treating it as a constant, minus. So this is with respect to x. Y is just a constant. So this becomes y squared. This is the first term right here, delta x, and we'll multiply it with 0.1, which is our error in x. Okay, so into, okay, plus, and of course we have to take the absolute value sign here. Don't forget that. That is very, very important. Plus absolute value, when we are differentiating with respect to y, this becomes x square minus 2xy. Now for differentiating with respect to y, we are keeping the x constant. We are just treating it as a constant. We are assuming it does not change at all, into 0.1. So this is our delta q, the net error in q. So with this, we can plug in the values of x and y, which is x is 3 and y is 2. So if you plug in the values right here, we will get delta q as, this comes out to be 1.1. Okay, very, very simple. We are just plugging in the values of x and y. Now things are simple. We can just plug in the values of x and y, and at this particular point when x is 3 and y is 2, our delta q becomes 1.1. That we already have. We can also substitute the value of x and y in this function of q. Directly substitute x as 3 and y as 2 in this function to calculate the value of q itself. So if you calculate the value of q, substitute x as 3, okay, so the x comes at 3 and y as 2, this q value, it becomes 6. So you can compute it, the value becomes 6, and this is the error, 1.1. So if we simplify this entire thing, this becomes 6 plus minus 1. Okay, so we keep the error only till one decimal place. That is the value of our final answer of q. This is what the q becomes. 6 is the value, and plus minus 1.1. We only keep the error to one decimal, one significant figure. So one significant figure means that we keep the 1, and of course we also keep the output, the value of the actual quantity, the value of q, to the same digit as we have kept the error. So error is in units place, so we will only keep the units place right here. So that's our final answer. So when we are dealing with multiple variables, we can simply extend our rule of differentiation, and we can divide the error into two components, into various components, one because of each of the variables, and the error due to each of the variables can be calculated by calculating its partial differentiation, by doing the partial differentiation, which gives us the rate, and multiplying it with the error in that particular variable. Okay, and we add those. So this is our general rule. If we have several quantities, a1, a2, a3, and the function z is the function of these several quantities, then the absolute uncertainty in z is the sum of uncertainties in each of the variables multiplied by the respective partial differentiation of z with respect to that variable. Okay, so very, very simple. This is a very simple rule, and if you use this, you can calculate the error propagation in any formula, in any of the formulas. So here, as an exercise, we have asked you to compute the value of refractive index in terms of the sine of the two angles. So that is roughly the application of Snell's law. So n is sine theta by sine r. Let's say that I have an error in I which is given by delta I, and I have an error in r which is given by delta r. You have to compute delta n in terms of delta I and delta r. So this is an exercise. We will solve it in the subsequent class. Thank you.